Welcome back, everyone. Engineers are returning to a forgotten idea that once seemed outdated. Compressed air energy storage is now being rebuilt from the ground up with precision monitoring and new materials. The principle of storing wind or solar electricity as air pressure is simple, yet its revival shows how modern computing and thermal science can make old concepts practical again. Across Europe, the United States, Japan, and South Korea, new projects are underway to build caverns that breathe in power when the grid has too much and exhale it when demand peaks. Please subscribe now. Deep below the surface, salt formations form natural spaces perfect for storing energy as compressed air. These domes are smooth, flexible, and self-sealing, which makes them safer than artificial tanks. Engineers drill narrow wells that lead to vast hollows hundreds of meters below. When cheap renewable power floods the grid, compressors force air into the cavern until the internal pressure climbs to more than 50 times that of the atmosphere. Later, when power prices rise, valves open and the compressed air escapes upward, spinning turbines and creating a steady current of electricity ready for distribution. For decades, the challenge was not how to store air, but how to manage the heat produced when compressing it. As air squeezes, it grows hot, and that energy used to be wasted. Modern systems capture it through insulated heat exchangers filled with molten salts or ceramic granules. These absorb thermal energy during compression and give it back during expansion. By recycling the heat, engineers raise round-trip efficiency from around 40% in early prototypes to more than 70% today. The captured warmth also prevents icing, which once caused older turbines to seize during cold discharge cycles. The earliest example of this approach came from a demonstration plant in Germany during the 1970s. That facility stored off-peak electricity from coal plants rather than renewables, but it proved that large air reservoirs could act as mechanical batteries. The limitations at the time were materials, sealing methods, and crude control systems. Half a century later, with precise sensors, high-strength alloys, and computer regulation, the same idea returns stronger. The project sites in Lower Saxony are being reactivated using digital twins that model every thermal and mechanical shift inside the rock as energy flows in and out. A digital twin is a complete computer model of the system that updates constantly through sensor data. Every pipe, valve, and turbine in a compressed air plant can be mirrored virtually, allowing operators to predict fatigue, leakage, or pressure spikes before they occur. Universities in Denmark and Japan are refining these simulation tools for energy companies that need millisecond accuracy. By linking digital monitoring with artificial intelligence, a single control center can manage many caverns at once. Each one can respond independently to grid signals, absorbing or releasing power in perfect synchrony with real-time demand. A key reason for renewed interest is scale. Batteries serve smaller roles, but a single underground cavern can hold energy equal to tens of thousands of lithium cells. A formation the size of an office tower may store hundreds of megawatt-hours of power for several days. This capacity makes compressed air storage suitable for stabilizing national grids. In Canada, teams are studying abandoned gas fields for conversion. The steel casings and boreholes left by extraction can often be reused. In South Korea, experimental rock caverns under industrial zones supply backup energy to precision factories that require steady voltage. Thermal energy storage is what makes this technology efficient enough for modern grids. During compression, some of the input electricity becomes heat. If that heat escapes, efficiency collapses. To retain it, air passes through layered tanks filled with molten salts or packed ceramic spheres. The hot air heats these materials, which can store energy for many hours. When the air is later released, it flows back through the tanks and reheats, regaining its expansion power. The design borrows from solar thermal plants and applies it underground, marrying two proven techniques into one stable mechanical system. Developers are also combining compressed air with hydrogen and other gases. At a test site in Italy, engineers split part of the incoming electricity to produce hydrogen through electrolysis. Some of that gas mixes with air to improve turbine combustion and recover additional energy during discharge. Others store nitrogen in separate compartments to reduce oxidation. By tailoring the gas mixture, designers can fine-tune performance for specific geology. This blending of mechanical and chemical storage hints at a future where multiple systems operate together rather than in competition, each covering the limitations of the others. Economic models for these systems show promise. While drilling and construction costs are high, the long lifetime spreads that expense over decades. Unlike batteries, compressed air storage does not degrade with cycles. Its only moving parts are turbines and compressors, which can be serviced or replaced without disturbing the cavern. Analysts estimate total operating life beyond 50 years. When measured over time, cost per kilowatt-hour drops below that of most chemical systems. Governments and private investors are taking notice, viewing the technology as infrastructure rather than experimentation. Long-duration storage brings long-term value. Noise and land use concerns are relatively small because most activity happens below ground. At the surface, a compressed air plant occupies little more space than a warehouse. Compressor buildings can be soundproofed easily. The air itself is clean and non-flammable, removing the need for special safety zones. Operators often locate facilities in existing industrial areas where transmission lines already exist. The visual footprint is minimal, making this form of storage politically easier to approve. Residents near pilot projects in Germany and France have reported no measurable vibration or noise beyond the plant boundary. Maintenance routines follow a predictable pattern. Operators perform daily checks on turbine bearings, pressure valves, and control circuits. Every few years, teams send robotic probes down access shafts to inspect cavern walls with laser scanners. Data from these inspections feed back into the digital twin to refine predictions. Because the air is dry and non-corrosive, damage accumulates slowly. Components like compressors and motors can be swapped in modular fashion. The result is an energy asset that behaves more like heavy infrastructure than a fragile battery field, demanding modest upkeep for massive capacity. Research collaboration continues among universities and companies worldwide. The University of Tokyo focuses on ceramic fatigue and thermal stability. École Polytechnique in France studies airflow turbulence inside curved tunnels. The Technical University of Denmark develops new turbine geometries optimized for variable pressure operation. In the United States, the Department of Energy funds test sites in Illinois and Oklahoma to integrate compressed air with smart grids. Polish and Canadian firms contribute automation software that coordinates multiple caverns through shared data links. The cooperation demonstrates how knowledge from many regions pushes forward a single global objective. Engineers are experimenting with isothermal compression, a process designed to keep temperature constant while compressing air. Using fine mist sprays or liquid pistons, the system absorbs heat as it forms, avoiding the need for separate thermal storage. Although still experimental, it promises efficiency gains that could approach 80%. An Italian startup called Energy Dome is pursuing a related idea using carbon dioxide in a closed loop. While the gas differs from air, the physics is nearly identical. Such innovations show how every branch of mechanical storage continues to evolve through creative adaptation. Education and workforce development are following the technology. Vocational schools in Europe are adding courses on mechanical energy systems, turbine maintenance, and geological modeling. Students learn to analyze seismic data and identify suitable formations for future projects. Universities are partnering with industry to create internships that place young engineers inside pilot plants. The goal is to build a generation comfortable with large physical energy systems as well as digital control. By 2029, many of those students will be operating full-scale facilities that they once studied in classrooms. Looking ahead, global potential for underground compressed air storage is vast. Geological surveys suggest that most countries possess at least some rock or salt formations suitable for development. Western Australia, parts of the Mediterranean, and the American Midwest have already mapped likely sites. If only a fraction were developed, total capacity could exceed current worldwide battery storage many times over. Governments see this as a bridge technology that can stabilize renewables until fusion or advanced nuclear designs mature. Mechanical storage fills the vital gap between generation and consumption with dependable predictability. Public communication is essential to keep these projects moving. Transparency about construction, monitoring, and safety builds trust with local communities. When residents are invited to tour surface facilities and see the quiet turbines firsthand, skepticism fades. Unlike chemical batteries, there is no disposal problem at the end of life. The caverns remain part of the landscape, ready for new uses. Some might later hold compressed nitrogen, or even serve as seasonal heat reservoirs. The concept of using underground space as an energy tool is expanding faster than anyone predicted a decade ago. By 2029, underground compressed air caverns could operate alongside hydrogen plants, geothermal systems, and advanced nuclear reactors as pillars of modern energy networks. They provide the missing middle ground between short-term batteries and long-term pumped hydro. Every advancement in compressor design or heat recovery brings the cost lower and the performance higher. What once seemed like an outdated mechanical idea is turning into a cornerstone of grid stability. It stands as proof that innovation often begins by improving something already known. Thank you very much for watching. Please like and subscribe.